Hello, and today we'll start the unit on coagulation. We've just been finishing the unit on our reactor theory, and hopefully now you'll begin to see how that fits in to what we do in the water treatment system. We begin by looking at a number of water treatment systems just so that you have a sense of how coagulation fits into the entire process. So this is an image from Drinking Water Guideline Manual for New Zealand, and you'll see a number of slides that I will include throughout this semester on regulations in New Zealand. I added those when I was on sabbatical, and I think they're useful for you to get a sense of how the regulations and how the processes or cons are applied in different settings. So in this case, we take raw water and we add a coagulant, and we'll talk extensively about what that really means. We want to mix that, what's referred to as rapid or flash mixing. We want to ensure that the chemical is evenly dispersed throughout the water to be treated. And then in some cases we will add additional chemicals, but that water then goes into a flocculation basin where it is slowly mixed to allow the particles to come into contact with one another, and then they can settle in the clarifier. This is another system. This is actually from the Severn Trent plant in the UK, and here it's slightly different. So we start with screening, and actually in the previous case there would also be screening. You want to remove any large material, twigs, fish, etc. from the water supply so that you're not harming the pumps as you pump that water into the plant. In this case, they add pH, or they have pH control, so they add either a base or an acid for pH control. They also add a oxidant or disinfectant. There may be multiple reasons for that. One could be, for instance, the control of zebra mussels, which is a major problem in much of the US. It could be for taste and odor control. It could also be as a disinfectant to try and prevent microbial growth in the subsequent processes. You can see here they add a coagulant to the rapid mix system. They then go through flocculation, sedimentation, and then further treatment, which we will talk about extensively throughout the semester. So we see in this system, this is actually in New Zealand. It's on the North Island of New Zealand. And in this case, this plant takes water from a lake and a river system. It also goes through filtration by screening initially, and then they add powdered activated carbon for taste and odor control. And then they do a pH adjustment with either lime or carbon dioxide. And that then moves into a rapid mix system, followed by coagulation, flocculation, and then further treatment. So one of the things I want you to think about throughout the semester is how in water treatment, when we're treating water or when we're providing water, we really think about it with a multiple barrier approach. So we think about source water protection. You want to make sure that either your lake, your reservoir, your groundwater does not become contaminated. So typically there will be some sort of a source water protection plan in order to protect that water source. And then we think about the wastewater treatment plant itself. You'll find that there are multiple barriers even within the water treatment system. And then we have the distribution system, and we want to ensure that that water is potable and palatable not only at the plant tap, but throughout the entire distribution system. So we can define a number of terms. We need to make sure that we recognize that these terms can be defined in multiple different ways, and it really depends on the discipline. The way we will define it is the typical approach that's used in drinking water treatment or really environmental engineering. So coagulation is referred to as the addition of chemicals to destabilize particles for flocculation. In the class this morning, I talked about milk. Milk is a stable colloid. However, if you leave milk in the refrigerator for a long time, forget about it in the back of the refrigerator, you come back, you look at it, and you find that you've got this clarified liquid on the top and this clumps of white material at the bottom. Basically what's happened is the bacteria have produced acids. They have destabilized the proteins and fats, which are colloidal, in the milk suspension, cause that material to settle out because they can aggregate together. So it destabilizes those proteins. They can stick together, they aggregate, and they settle. And you end up with a clarified liquid on the top. We can essentially do the same thing in a water treatment system. Flocculation is then the process of bringing these particles together. So we want to change the nature of the particles in some way that will allow them to come together. When they come together, they stick together. Flocculation is the process of bringing the chemicals together. And then once these particles aggregate, we want to remove them. So there's a number of physical methods we can use. These range from sedimentation, so allowing the material to settle, to flotation, where we actually bubble material to the surface, or filtration, where we use some sort of media, membrane system, a granular media to remove that large material. So coagulation flocculation is designed to remove a number of types of materials. These include microorganisms. They include toxic compounds that are sorbed to these particles, and the bacteria may also be sorbed to these particles. And they also remove naturally occurring organic matter, and that is these are a precursor of disinfection byproducts, so we want to remove this material for that reason. What we're attempting to do is to make water more palatable and more potable.
Here are 2 beakers filled with the same amount of muddy Charles River water. On the left is our control, which will remain untouched, and on the right, we'll add 3 milliliters of prepared flocculant solution. Then we'll stir for 2 minutes and wait. Wow! What just happened?
So what did just happen? What happened was that a coagulant was added to the colloidal suspension from the Charles River, and that caused the particles surfaces to become neutralized so that when the particles come together, they could aggregate and then they eventually would settle out.
So when we're looking at coagulation, a number of things we need to recognize. One is that the charge on most colloidal material in a natural system is negative. So this, just want to emphasize, this is in a natural system. So we're looking at colloidal material in a natural system. So this can be, as is shown here, this can be bacteria, this can be viruses, it can also be clay, very small clay particles. So we're looking at removing this. Now, if we have what's referred to as a stable suspension, so as I mentioned, milk is a stable suspension, the particles repel one another so they stay in suspension. They're not going to aggregate, form large enough particles to settle out. So a stable suspension is one where the particles repel one another so they don't aggregate. And we can show this with schematic here. So we can think of this as these clay particles. They're negatively charged. If we can neutralize that charge, then these particles have the potential of aggregating, sticking together when they contact one another. And there's a YouTube video if you want to watch that later. So as we discussed this morning in class, when we talk about colloidal dispersions, we typically discuss it in terms of what is referred to as DLVO theory. This is just a theory developed by three researchers. Last names begin with D, L, and B, and O. And what they looked at is they looked at the interactions between van der Waals attraction and electrostatic repulsion of the particles itself and the counter ions. So what do we see here? We see that we have a particle, and we've got a negatively charged particle. We have positive counter ions in solution. We refer to this first layer, this dense layer, predominantly of, in this case, positive counter ions, as the stern layer. So this is the stern layer. And then we have an electric double layer out here. So stern layer typically is quite thin. It's about 500 angstroms thick. Your electric double layer is much thicker and can be up to about 300 angstroms. And then out here we have the bulk solution. Okay. Now typically when we're looking at these systems, we will often measure what's referred to as the zeta potential. You can think of that as the electrostatic potential of the system at some point in this theoretical schematic. And the zeta potential is measured at this point here. So it's into the double layer, but very, very close to the stern layer. And it's important because it gives us a sense of how well these particles will aggregate. So as I mentioned, the DLVO theory looks at a balance between the repulsive electrostatic forces and the attractive van der Waals forces. And we're looking at particle stability depends on a balance between those. So if we look here at repulsive curve, what they refer to as repulsive curve 1, what we see, okay, we have the attractive forces between these particles. And what you see is that the electrostatic force, or the potential energy, drops off with distance from the two particles. So basically, as you get further and further apart, the repulsive forces decrease, which you can expect that. If you think about a magnet, as you bring the magnet together, if you get close enough, you can actually sense those repulsive forces if it's the both end of, for instance, the north end. And as you pull them apart, the force becomes less. Now the attractive force doesn't change significantly with distance. So if we look at this with the repulsive force here, so with net energy 1, so if we're looking at this one here, we see here that there's a net repulsive force. So when we bring these two particles together, they will tend to repel and we'll have a stable colloidal suspension. On the other hand, we have this curve here. So we'll draw that with a blue line. The attractive force doesn't change here. And what we have, this is our net force here, and notice it is close to 0. So here, when we bring the particles together, they don't repel, they will tend to stick together. We can show that again here, and we talk about the compression of the electric double layer. And this is just another schematic essentially showing the same thing. So what do we have here? Again, it's shown this morning. We have a double layer repulsive force. We have the attractive force, and again you can see the net repulsive force, and we have a stable suspension. And then in this case here, we have a double layer repulsive force here, and we have our attractive force, and again you can see here where we have a net 0 potential energy, and we have an unstable colloid because these particles, when they come together, they will tend to stick. So we can look at the effect of counterions on this compression of the double layer. And one of the things we find is that increasing the charge on the counterion decreases the electric double layer thickness. So if we start with sodium, and then we look at calcium and, for instance, aluminum. Okay. As we increase the charge, what we're going to see is a decrease in this electric double layer thickness. So if we were to look here, if we look at sodium, for monitoring this plotting the repulsive forces, we'd have sodium out here, we'd have calcium here, and aluminum here. Okay. We also note that the ionic strength that results in the reduction of the electric double layer to the point where flocculation occurs is referred to as the critical coagulation concentration. So that's how much coagulant we need to add in order to reduce this electric double layer to the point where the colloids can aggregate together. And we find that the critical coagulation concentration is a function of the charge to the 6th power, which means that charge plays a very, very strong role on the amount of coagulant that we need in order to destabilize these colloids. When we do, that means that we've overcome the repulsive forces, and as I mentioned, that's where flocculation will occur. So we can see this in this plot here, where we start with a solution of 10 to the minus 3 molar, 10 to the minus 2, and 0.1. So we're increasing the concentration by a factor of 10 each time. And you can see here, and you can think here, if we're looking at the thickness of an electric double layer, it's much thicker in the more dilute solution. Think about it, you need more counter ions in order to neutralize that charge. So the EDL is larger. And then we decrease it to 0.0, or increase it to 0.01, and we decrease the thickness, and here we increase it again, and we have further decreased the thickness. So that 0.1 is going to destabilize that colloid much more effectively than the 10 to the minus 3 molar solution. And here we look at charge. So you can see if the charge is 1, our thickness of our electric double layer is quite thick. If we increase the charge to 2, so this is charge of our counter ion, then that decreases the electric double layer, and then we can further decrease it by increasing the charge to 3. So again, this is the charge of your counter ion. And what we're looking at adding, if we have compression of a double layer, then this is the ion that we're adding. So for instance, in this case, we don't use sodium chloride as a coagulant because it's not very effective. But if we did, that would be charge of 1. We could use calcium. Calcium bicarbonate as a coagulant, and we use aluminum sulfate or alum as a coagulant. So we're adding aluminum ions. So we'll stop there, and we will continue talking about coagulation on Friday.